Welcome everyone. So today we're going to discuss about Lagrangian and the Euler-Lagrange equation. So Lagrangian and the Euler-Lagrange equation is a fundamental concept in physics and in the calculus of variation. Here the Euler-Lagrange equation providing a second order differential equation that describes paths or fields that maximize or minimize action functional. To discuss about the Euler-Lagrange equation, we need to start with the Lagrangian. So here the Lagrangian L is a function typically of kinetic energy T minus potential energy V. So we define Lagrangian in this way, that Lagrangian L is equals to T minus V. Here T is the kinetic energy and V is the potential energy. Now the Euler-Lagrange equation. So derived from the principle of least action, it states that for a system's motion or evolution, the partial derivative of the Lagrangian L with respect to a coordinate q minus the total derivative with respect to time of the partial derivative of L with respect to the generalized velocity q dot must be 0. So del L by del Q minus ddt of del L del Q dot is equals to 0. So here Q is the generalized coordinate and Q dot is the generalized velocity. So del L by del Q minus ddt of del L del Q dot is equals to 0. This is the Euler-Lagrange equation, and here L is the Lagrangian of the system. So this is the Euler-Lagrange equation, and it effectively reduces the complex force problem into simple energy based problems. Now we are going to consider one example. Okay, now so we are going to consider one example and we are going to take the simple pendulum. So in case of simple pendulum, the coordinate q is theta. So in case of simple pendulum, we take theta as our generalized coordinate. So theta is q here, and the kinetic energy T is half m L square theta dot square, and the potential energy V is equals to mgl into 1 minus cos theta. So the Lagrangian, as we know, the Lagrangian is T minus V, that means the kinetic energy minus the potential energy. So Lagrangian L will be equals to half m L square theta dot square minus mgl into 1 minus cos theta. So this is our Lagrangian. So following the Euler-Lagrange equation, we can write it in this way, that ddt of m L square theta dot plus mgl sin theta is equals to 0. So the final equation of motion, if we do this derivative, then this term will be m L square theta double dot plus mgl sin theta is equals to 0. Now we are going to eliminate this m L square term or divide this term with m L square. Then our final equation will be theta double dot plus g by L, because m L gonna cancel out, so plus g by L into sin theta is equals to 0. So our final equation will be theta double dot plus g by L sin theta is equals to 0. So this is our final equation in case of simple pendulum. Advantages of using Euler-Lagrange equation or Lagrangian mechanics is that sometimes it is easier to write down Lagrangian rather than forces, and if we use Euler-Lagrange equation, it simplifies our complex problems into simpler problem, and also the conservation laws appear immediately, and the Lagrangian mechanics is the gateway to modern physics. So these are the advantages of Euler-Lagrange equation. So today we have discussed about Lagrangian and Euler-Lagrange equation, and on our next class we're going to discuss about Hamiltonian. Thank you everyone.